Today we are very happy to have Dr. Pamela Cambianca giving a talk on her study on the comet 67P, and she's an expert on the dust of the comet 67P, which was the target of the Rosetta mission of ESA. And she got her degree, PhD degree from Padua, and she's now working on PP Colombo, which is a mission going to Mercury, and we will arrive at the target at 2025, right?
Yeah. Right, exactly.
So you're very busy now.
Yes.
And once arrivals, because Pamela working on the experiment, on the camera experiment, very interesting, very important camera experiment, and will tell us a lot of new things about Mercury, which is the innermost planet. And we hope to invite her back to give us the talks, on Mercury. 2025. So it's a promise, right, Pamela?
Yes, okay, I promise.
Okay, good. So then today we will hear what she talked about, what she found at Comet 67P. Okay, good. Let's start. Please do. Yes. Please.
Right. So first of all, good afternoon, everyone. So I would like to really thank you for giving me the opportunity to speak about my research. And as has already been mentioned, I'm a postdoctoral research scientist at the Astronomical Observatory in Padova. And my background is astronomy and in particular planetology. In 2016, I won a PhD fellowship about the Rosetta mission and in particular about the OSIRIS instrument that I will show you later. And the aim of my research was to contribute to the research dealing with the cometary formation and the devolution. So this is the reason why today I would like to focus on some results we obtained, which are about the seasonal evolution of dust deposits on this amazing solar system object. Okay, great. So let's start. So this is the agenda of my presentation. First of all, I will giving you a very quick overview about the world of comets, and I will go into the detail talking about the Rosetta mission and its target, Comet 67P Churyumov-Gerasimenko. And then I will briefly present the so-called mass transfer mechanism, and then I will go into the detail of the work I want to introduce you today by speaking about the selected regions and the tool we developed to measure and to quantify the seasonal evolution of dust on Comet 67P. And finally, I will show you the results and conclusions. Okay, so in these two pictures, you can see what a comet seen from the Earth looks like. So the tail represents the main element that is associated with a comet in a collective imagination. But in reality, what is a comet? So a comet is an orbiting celestial body made up of very different things: ice, gas, organic compounds. It's a very complex celestial body. And it consists of three main parts. The first part is the nucleus, which represents the solid part of the comet and is what you cannot see from the Earth. Because approaching the sun, as you are aware, the heat received causes ice to sublimate and gas to expand. And this phenomenon is responsible for creating both the coma and the tail around the nucleus. So looking closely a little bit to the structure of a comet and starting from the nucleus, we can say that a comet is made up of interplanetary particles, dust particles, such as diamond, graphite, silicon, and so on, and frozen gases, such as CO, water, CO2, and many more. Then, approaching the sun, the ice on the surface of the nucleus transforms into gas, sublimates, forming the coma around the nucleus, which is basically a sort of envelope made of dust and gases surrounding the nucleus. Then, and finally, tails. Tails form because radiation from the sun pushes dust particles away from the coma, while charged particles convert gases into ions, forming the ion tail. So we have basically 2 or 3 different tails: dust tails, ion tails, and sometimes sodium tail. So both tails point directly away from the sun, and they show 2 different colors. The dust tail is appeared to be yellow or white because the dust reflects the sunlight. On the contrary, the ion tail contains frozen material, including carbon compounds, which absorbs sunlight and fluorescences. And this is the reason why the ion tails appears to be blue. But the main question is why it's so important for us to study comets. The reason is that they are considered as leftovers of the solar system formation, and they are reminders of the material formed in the coldest part of the solar system. And this is for this reason is fundamental to study them, to understand a little bit more the formation of the solar system itself. This is very important. This is the reason why the European Space Agency decided to design a very important mission. The European Space Agency Rosetta mission, as you are aware, this was the first mission designed to orbit and land on a comet. So during the first 6 months of observing Comet 67P, it became immediately evident that this small body was anything but a simple dirty snowball, and the potential of this mission became immediately apparent. So the space probe was launched in March 2004, and during the cruise phase, the spacecraft observed 2 different asteroids, Steins and Lutetia. And then Rosetta entered in deep space hibernation phase in 2011 and reached its target in August 2014 after 10 years journey. Then on 12 November, the spacecraft released the Philae lander for the first touchdown on a comet nucleus. And as you know, this event was not a very easy task because there was a lot of bounce. But finally, the mission was concluded very successfully on 30 September 2016 with a very controlled impact onto the surface that you can see here in this video. The Rosetta spacecraft was a box structure with 2 long solar panels and a 2-meter parabolic antenna, and 11 instruments was on board the orbiter, including remote sensing, radio science, instrument for the analysis of composition, mass distribution, dust flux, and so on and so forth. It was a very complex orbiter. And as I said at the beginning of the presentation, the aim of my work was to analyze data coming from the OSIRIS instrument. And the OSIRIS stands for Optical and Spectroscopic Infrared Remote Imaging System, and was designed to image the comet nucleus, its gas and dust coma. And it consisted of 2 different cameras, high-resolution cameras, in particular a wide-angle and a narrow-angle cameras with spatial scales of 10 and 1.86 meter per pixel from 100 kilometers respectively. And this allowed to take very high-resolution images of the surface of dust and gas of the comet. And the wide-angle camera was designed here and developed here by the University of Padua. And this was the target of the mission. The comet is composed of 2 different hemispheres connected by a neck called HAPI, that I will show you later in detail. And the comet appeared immediately rather dark, reflecting only 5% of the incident light. And this comet was classified as a Jupiter family comet. So it's a short period comet, which takes about 12 hours to rotate around its axis. And one of the most important things is that its obliquity, the obliquity of its axis, was about 52 degrees. And this obliquity was responsible for the strong seasonal effects experienced by the comet. And I will show you later the reason why it's so important, this number. And finally, the comet can be considered a sort of collection of contrasts because a huge variety of terrains, landform, and features can be found on the surface. You can find, for example, smooth or hammocky terrains, partially or entirely covered by dust, but also you can find pits, vertical cliffs, boulders, and many more. And one of the most important features for this work, in particular, is the morphological dichotomy between the two hemispheres. In fact, the two hemispheres, as I will show you later, appear very different. Southern regions are characterized by the presence of consolidated and coarse terrain and are dust-free, basically. On the contrary, the northern regions show terrains fully covered of dust. So we decided to investigate the reason why the two hemispheres appear so different. Okay, so now I'm going to introduce you the so-called mass transfer mechanism. It's a little bit complicated, but I will try to explain clearly, I hope. Due to the obliquity, as I said, due to the obliquity of the comet's rotational axis, Comet 67P experiences strong seasons, resulting in significant differences in insolation between the two hemispheres. So this strong dichotomy in terms of insolation is reflected in the morphology between the two hemispheres. So in particular, southern regions, which are characterized by consolidated and coarse terrain, are characterized by strong insolation since southern summer correspond to the perihelion. And this results in a very strong erosion, up to 4 meters, of the surface and a very strong water sublimation. This is the reason why we can find consolidated and dust-free terrains. On the contrary, northern regions are characterized by the presence of dusty terrains since they are characterized by a very minimal amount of insolation and then a very minimal erosion of the surface. This is basically the main difference between the two hemispheres. For this reason, in 2015, Keller et al. Proposed the mass transfer mechanism. So the dust cover, the idea is that the dust cover in the northern region can be the results of the mass transfer mechanisms, basically the particle ejected from the southern hemisphere during the southern summer are transported in the northern region. And here you can see on the right side that the erosion can reach its value of about 4 meters. So these dust and chunks are ejected from the southern hemisphere and then are transported in the northern regions. Now, the mass transfer mechanism is a little bit summarized here in this graph. So, starting from the perihelion. So during perihelion, the southern regions are characterized by a strong insolation, as I said, and a consequent strong erosion. The nucleus starts to eject dust and chunks. Chunks are pebbles of from 10 to 25 centimeters size. And as a result, the southern terrains appear to be dust-free. Then chunks fall back over the whole nucleus. And after the outbound equinox, the southern erosion decreases. So after the perihelion, the southern erosion decreases, and the insolation and erosion in the northern regions remain minimal. Finally, the phenomenon of outgassing occurs. So we have the erosion, the fallout of the material, and the outgassing phenomenon. During the outgassing, we have a sort of dehydrated crust above chunks. And the dehydrated crust above these elements is removed due to the migration of ice to the surface from the center of these chunks to the surface. And the fallout is then self-cleaned. So the conclusion of this phenomenon is that the dust cover in the northern regions can be the results of transport mechanisms of particles from the southern hemisphere during the southern summer. And then we have a sort of outgassing and self-cleaning of the fallout after the perihelion passage. And this IRIS instrument was fundamental to study, for the study of these mechanisms, because thanks to the high resolution, allowed to recognize and study a huge variety of surface granularity from dust to chunks, so from 1 up to 25 centimeters in size. Another very important aspect related to the mass transfer mechanisms is the possibility to link, to investigate, and calculate the refractory to ice mass ratio of the nucleus. So, as you know, as you are aware, Comet 67P is composed of 2 different hemispheres connected by a neck, which is called the HAPI regions that you can see here. HAPI is the conjunction point between the 2 lobes and shows a very peculiar morphology and is considered as the preferred location for the accumulation of material coming from the southern hemisphere. It's a sort of reservoir of chunks due to the morphology, and was considered as the most active area during the northern summer. And it never shows a very strong outburst, but a modest continuous activity from far from perihelion. So we decided to start from these regions, and the activity of these regions is due to a very thinner desiccated dust layer which accumulates after perihelion because of the fallout of the material coming from the south. And is eroded, this thin desiccated dust layer is eroded by the ice sublimation when the comet approached the sun after perihelion. So, HAPI's outgassing activity started from 2.4 to 4 AU outbound, and it was negligible elsewhere. This region ejected sub-centimeter dust only, and acted as chunk deposit coming from the southern hemisphere. So these chunks showed an upward exposed dehydrated crust, as I have already said, and the dehydrated crust above the chunk is removed from the migration of ice to the surface. So the thickness of this crust is strictly related to the refractory to ice ratio. In fact, the thickness of the crust increases as the ratio increases. So this is the results. Fresh ice is exposed by water migration from the center to the surface of chunks, and by the removal of this dehydrated crust, outgassing from the interior of chunks were visible, of course. And the deposit of this material, of these chunks and dust on the surface of the nucleus prevented any outgassing from below the surface. And this is the reason why we never seen a very clear ejection of dust from these regions, but just a continuous ejection of dust. So we started to think about how to quantify and measure these mechanisms, the transport mechanisms. After observing these images, in which it's quite evident that the dust in the image on your right has been, the dust in the image on your right has been removed. We developed a tool to measure the height of a boulder simply by measuring the length of the shadow projected on the surface, because as you can see here in this sketch, any height variation is not due to boulder intrinsic changes, such as erosion, for example, but to erosion and the creation of the surrounding dust deposits. So we developed this tool, and After the implementation of the SPICE kernel's data about ephemeris and the location of the comet with respect to the OSIRIS instrument and so on, we selected the 19 high-resolution OSIRIS NAC images with a spatial resolution of at least 1.30 meter per pixel. We selected the 22 boulders located in the HAPI region, and we used the 19 OSIRIS images starting from 21 August 2014 up to the end of the mission in September 2016. So after the selection of the proper image, we needed to align the image with a 3D shape model because we needed to correct the projection of the image. And this can be achieved simply with a definition of single type points, both on the shape and on the image, and with an application of a transformation, a proper homography transformation between the two systems, the image and the shape model can be aligned. After that, we defined a local surface around the boulder, the selected boulder, in which the shadow is projected to avoid any kind of granularities of the surface, both of the mesh and of the terrain. The right definition of the plane, which is called the sigma plane here in this image, allows to define the normal, the n vector, to the surface without considering such irregularities in order to calculate the correct incidence angle. So basically, we simply need the length of the shadow and the incidence angle. Finally, after the selection of the peak of the shadow, which is represented here by the red arrow, the tool returns the projection of the length of the surface. And in the next slide, you can see the profile of the boulder. This is the output of our method, of our tool. So basically, we can clearly distinguish the profile of the boulder with respect to the sigma plane that we defined before. And we can measure the height of the boulder. Okay. Now, I'm going to show you the first part of the results we obtained and published in 2020. So, as I said, we focus on the time evolution of dust in the HAPI region because, as I said, was a very peculiar and active region. And we started from this area, but I will show you later that we applied also to other 3 different regions the same method. So in this picture, the average height measurement for each boulder can be found. As I said, we selected the 23 boulders of the HAPI region, and as you can see here, we notice that each boulder shows the same trend. Its height increases before the perihelion and decreases after the perihelion. The height increases means that we have a sort of erosion of the surface, since our assumption is that there are no erosion of the boulder itself. And a decreases of the height corresponds to a outgassing of the surface. And in the next slide here, the difference between the height measurement of a generic image and the height measured on the first image we used on 21 August 2014 is shown as a function of time. And we find a systematic increase of height, as I said, of about 2 meters over 2014, and then a decrease by a similar amount between the equinoxes, followed by a sort of plateau, as you can see at the end of the observations. Okay, the assumption here is the same. Any height variation is not due to boulder intrinsic changes, but the erosion or accretion of the surface and the surrounding pebbles and dust deposits. And the measured decrease of the boulder's height at the perihelion phase from 2014 to 2016 of 1.4 meter, which is basically 1.7 minus 0.3, has been interpreted as a direct measurement of the fallout thickness. In fact, this value matches the predicted fallout thickness of 1.8 meters by Full et al. In 2019, revealing a clear consistency between the perihelion erosion and the total loss of nucleus mass per orbit. So basically, we confirm that the mass transfer mechanism consists of an erosion of the surface followed by a deposition of dust. And between June and September, between June and September 2016, the height variations are lower, as you can see here, than their error bars. And this is consistent with negligible fallout and erosion after the outbound equinox. And this finding is consistent with the process that has been suggested to be the main driver of the fallout, namely basically the expelled chunks in bond orbits are lowered by the friction with the coma gas and finally collapse into the nucleus. After the outbound equinox, basically, the coma of 67P is too tenuous to further affect the chunk motion. So we have a sort of plateau after the perihelion passage. Next slide. This value of 1.4 meter in erosion has some implication in terms of the amount of pristine ice. The measured erosion of 1.4 meter has been compared to the volume loss rate measured in the coma in the same period. And this allowed us to calculate the percentage of the fallout of material in the happy region due to its morphology. And this value was about 96%. So 96% of the eroded material fall back to the nucleus. Then we applied the fallout versus ice content model developed by Full et al. In 2019, and we calculated the HAPI's water ice fraction, which was about 2% as upper limit. This number, 2%, corresponds to the lower value of the refractory to ice ratio of 6, which defined for the first time the content of pristine ice in comet 67P. So from the measurement of the erosion, we quantify the amount of pristine ice in the surface of the comet. Finally, we decided to apply the method to other 3 regions of comet, and we published these results in 2021. And we selected 3 different regions. We selected the Maat region, which is located to the north, and the Imhotep and Hatmate regions, which both extend across the equator. And the reason was that this allowed us to compare the 2 hemispheres involved in the mass transfer mechanisms, and we compare the results. So for the analysis, we used 20, 31, and 14 OSIRIS-NACC images respectively. And we measured the height of 43 boulders, including the happy region. The analysis covers the period from August 2014 inbound the perihelion to September 2016 outbound. And the analysis is clearly limited by the fact that we needed images with a resolution of 1.30 meter per pixel at least, and with a similar observing conditions of the happy region to compare the results. Okay, these are the results. So, as I said, as regard the happy region, we found an erosion of about 1.7 meter during the inbound orbit, which nearly balances the deposition of 1.4 meter outbound from the southern hemisphere. And we found the same trend, as you can see here in this image, in this figure, we found the same trend in the Maat region with an erosion of about 1 meter and a deposition of 0.7 meter. And this is reasonable because both regions are located in the northern hemispheres. And actually, we expected the same trend, and we confirmed that the northern regions are characterized by this trend, an erosion followed by a deposition after the perihelion. On the contrary, here you can see that Imhotep and Hatmate regions located in the southern hemispheres show a very negligible erosion inbound and a similar erosion outbound of 0.3 and 0.2 meter respectively, because they extend across the equator. So next slide, the next one, in conclusion. In conclusion, so we developed this tool to quantify the seasonal evolution of HAPI, ATMate, Imhotep, and the MAT deposits erosion accretion with a vertical accuracy of 0.2 and 0.4 meter. And we compared the deposits in the HAPI region of about 1.4 meter with a volume loss rate measured in the coma in the same period, and we found a percentage of the fallout of 96% due to the peculiar morphology of the HAPI region. By applying the fallout versus ice content model, we found no, please go to the back to the slide. Thank you, to the previous slide, okay. We applied the fallout versus ice content model, as I said, and we found the HAPI's water ice fraction of 2% as upper limit, allowing us to define the lower limit of the refractory to ice ratio, which turned out to be 6. Then the MAT regions behaves like the HAPI regions. The MAT region is located in the northern regions as well. And by comparing the temperature of the nucleus surface, this is one of the most important things of the second part of this work, we found that by comparing the temperature of the nucleus surface, we found that all regions close to the neck reaches values as high as 230 Kelvin in August 2014. And our results confirm that the dust is ejected when the temperature is larger than 205 Kelvin. And we also confirmed that the fallout of perihelion is about 70% of the eroded material. So basically, one of the most important findings here is the temperature at which the nucleus can eject dust, and in this case is larger than 205 Kelvin. And finally, by checking the temperature of the nucleus surface, the Imhotep and ATMate regions show a temperature lower than this threshold of about 194 Kelvin, which is lower than the minimal threshold, as I said, and which is at which the dust is ejected. So this explains exactly the negligible erosion we found inbound the orbit. So the erosion outbound has been interpreted as a direct measurement of the fallout self-cleaning mechanism. And this allowed us to quantify for the first time the mass transfer mechanisms. And with this, I really thank you. I know that there are a lot of information, a lot of things, numbers, and but I hope it's clear, basically.